Our next speaker is Jerry Zhu from University of Wisconsin-Madison. He's going to talk about machine teaching for interactive learning. I think it'll connect well with some things that Tom started to talk about this morning. So, Jerry, take it away.
Okay, thank you, Rob. So my talk is going to be almost the opposite of what Tom did. Instead of very advanced frontier kind of natural language processing interaction, I'm actually going to start from something really, really basic, but in doing so, hope to build on some of Tom's questions in terms of sample complexity and so on. So let's start from asking the question, like, what we really want from the user. If we have a learning algorithm, I would argue that we want good teaching signals. So let's look at a very simple example just to get things straight. Imagine we're doing binary classification, and the input space is super simple. You have the interval 0 to 1, that's your X space. The labels are binary, and your hypothesis class consists of all the threshold classifiers at some theta. Okay, so Y is, let's say, -1 when it's less than theta, and bigger than 1 if it's bigger than theta. Okay. Importantly, let's use theta star to denote the target threshold. So that's the kind of thing in an interactive setting we say the teacher wants the learner to know. Okay, so the teacher is a human, and we want to train the learner. Okay. So let's contrast three types of teaching. The first one is simple. It's just passive learning, where the teacher would simply sample a bunch of n items, IID, say uniform 0, 1, and label them according to theta star. So let's assume it's noiseless. The label is always correct with respect to theta star. Okay. Now, if you are the learner, you get a batch of n IID samples. We know what will happen. Since it's noiseless, the true theta star must be in the middle, in the interval between the innermost positive and negative items. So the standard question people ask in packed learning is, well, how do you expect if your learner estimates some theta hat somewhere in the middle, how do you expect that theta hat to be away from the true theta? And intuitively, this quantity has size 1 over n, and it's easy to understand because if you think of all the n random training items, not as random, but just on regular grid of n items, then each small chunk is of size 1 over n. Okay. So we get this. That's the standard learning rate. And if you want this to, say, be below a precision of epsilon, you can conversely say we must teach with more than 1 over n examples. Okay, so that's standard passive learning. Now, most people here would say, well, we can do much better if we do active learning, and that is true. In active learning, the standard setup is the learner gets to pick X and query a human oracle for the label. Okay, again, it's noiseless. So for this particular task, active learning actually is binary search, where the learner would simply query the midpoint of the range first. And let's say the human says, hey, it's negative. Then it cuts off the left-hand side, and it's going to ask the next query, which is the middle of this, and so on and so forth. So as you can see, by doing so, every time the learner can cut off half of the hypothesis space, therefore, after n queries, we're very close to the true target. So it's 1 over 2 to the nth, or conversely, if you want a precision of epsilon, you need order of log 1 over epsilon. So to give you a sense, if you want epsilon to be 10 to the minus 3, in passive learning, you would need roughly 1,000 examples. Active learning here, you need 10 examples. Okay, but let's see, we're talking about interaction and teaching, right? So what if there is an ideal human teacher? Now, the ideal human teacher can say, hey, if I know the learner is simply a passive learner, and it's going to pick any theta star in the version space, which is the interval between any innermost positive and negative items, and the teacher knows that learner, the teacher knows theta star, the teacher has the ability to design a training set. So this is different. Design a training set or design a demonstration of items. In this case, clearly, the teacher can say, hey, I'm going to give you 2 items, epsilon away from the decision boundary. And I achieved my teaching goal. You as a learner, you didn't know that this training set is not an IID sample. You would just do your standard, cut away your vision space thing. You will arrive at a good hypothesis. And in particular, no matter what the required precision epsilon is, we only need 2 examples. Okay. So this is very different than machine learning. Okay. With that example, here's the plan for today. We're going to talk about why this matters. The study of optimum teaching gives us clarity as to what an optimum teacher can do. If the optimum teacher is ideal and can do all the good things, we will see that. So it comes, I should warn you, it comes with very strong assumptions. But it gives us some theory about what you can expect in terms of, the best teaching that you can possibly get, the computer can possibly get from a human teacher. So that's the first part. And then in the second part, I'm going to, of course, say the world is not ideal. You would not normally get a idealized teacher. So what do we do in that case? Okay, so let's move on to the first part, optimum teaching. The message I want you to bring home is treat humans as teachers, not just annotators. Okay. So what can an idealized teacher do for you? In this talk, I'm going to build upon all these very strong assumptions. Let me unpack them. So the first thing is the teacher knows the target model. So denoted as theta star, something that the teacher wants the computer to learn. Okay. Second, what's the ability of this teacher to create a training set? Okay. So I'm going to distinguish 3 kinds of abilities. The first one, I call it constructive teaching. Okay. In this case, the teacher can create a training set D. I'm going to use classification for most of the talk. And that's going to be in this capital D, which is a fancy way to say the union of n being 1 to infinity, x, y cross. This is just a way to say the teacher can create a training set of arbitrary size, any n. Okay? And it can use any item in the input space x and to label it as anything y. So that's what I mean by the teacher can lie, in that the teacher can give y labels that's not truly according to our target theta star. Okay, so this is a very flexible teacher, has a lot of ways to construct training set. The second kind of teacher is, well, an honest teacher. He's restricted in that he can still choose any x from the input space and use any training set size, but the label must be according to the true target. The third kind is even more restrictive. In this setting, the teacher cannot arbitrarily choose anything from the feature space. He has to work with a given and fixed pool of candidate teaching items. Okay, so this is very similar to something known as pool-based active learning. And here it's just pool-based teaching. He has to select teaching items from a pool. Okay, so that's that. Furthermore, we're going to assume that the teacher knows everything about the learning algorithm. So I'm going to use A for that learning algorithm. Now, the way I'd like to think of a learning algorithm is to think of it, at least for deterministic algorithms, as a function mapping from a training set to a concept, or rather in this case, it's a subset of concepts. So it's going from a training set to something. And let me give you 2 examples. One is our famous version space learner, where A given a training set D would simply give you back the subset of hypotheses that are consistent with the training set D. Or this one may be more familiar to people in modern machine learning. Given a data set, the learner simply runs regularized risk minimization for some loss function L, and there is some regularizer that may depend on a norm. And in this case, argmin returns the set of minimizers. So these are very strong assumptions, but it helps us to set up the problem. And with that, I'm going to show you a bunch of things. So here is the first formalization of what are we trying to do with teaching. So I call it special teaching because there are two things that's special. One is the teacher is solving a minimization problem, but note, it is solving it in the space of training sets. So it's going to be a discrete optimization problem. And the objective is simply the size, the cardinality of that training set. Okay, so that's one thing that's special about it. The constraint says, well, if I take that training set, give it to my learner, the learner should give me back the target model, okay, or at least contains the target model. So that's the second thing special about it. So the first one is it's trying to minimize the cardinality. Second, it insists that the student learns exactly. Now you can visualize this with the figure here, where here is the space of training sets. Any training set maps by this function or learner A to a hypothesis, and this should be big H. And therefore, given that the teacher wants to teach some theta star, there may be a subset of training sets that will result in theta star, and among which the teacher is going to pick the one with the least cardinality. Okay, yes, Rob?
Just, I mean, if the training set was empty, wouldn't A just map to the entire hypothesis space?
Well, it depends on, that's a good question. So if A is the version space learner, yes. With an empty D, AD would be H. If A is this, with an empty training set, you don't have this term, and you have a norm minimizer, so you would actually get the zero vector usually. Okay, so it depends on A. That's a very good question, and this shows the dependence. I should mention there's an alternative view, which is to say, hey, this is just doing coding, where the teacher has a message, theta star, the target model that he wants to send to the student. The student is a decoder, and that's interesting because we have a very strange decoder. It takes a training set, maps to a model. The language is in the set of training items. Okay, so special. This is an even more special case where I should say this is the great work by Goldman and Kearns in '95, where they defined the notion of teaching dimension and so on. But I should point out that the restriction there is stronger in that A is the version space learner. And usually all the quantities are finite, so it's easier to study. But the main concern there is really to say how large is the training set that you must have. Yes?
So I guess back to Rob's question, do you mean theta star is equal to, or AD returns the singleton set theta star in the version space case?
In the version space case, AD would simply be the whole version space.
So the solution to the optimization problem you put up there would be all of A, would be the empty D on the next slide.
Right. So let's see. I think you're right, and this is my mistake. In that case, we want theta star, the singleton set theta star, to equal AD. Thanks. Okay, so coming back to this, the objective function of the problem is known as the teaching dimension of the concept theta star with respect, actually, to the hypothesis space, big H. Okay. So this is the notion of minimally how many training example would you need in order for the learner to get that theta star. And then you could also define the teaching dimension of the whole hypothesis space as just being the hardest one in there to teach. Okay, so that's that. Now, teaching dimension is known for several concept classes. And interestingly, as I will show some examples, teaching dimension is different than the notion of VC dimension. And the connection between the two are actually somewhat tenuous. So we will see. So here comes, yes?
Does that depend on the algorithm that you choose?
It does. And here we are really using one specific algorithm.
Right.
So that's going to be the version space.
It's only defined for the version
It's
space.
only defined for the version space, at least for the classic teaching dimension. Yep. So let me see. I'm actually going to immediately move ahead with from your question. So the classic teaching dimension is defined only for version space learners. In this example, I'm going to move to other definitions of teaching dimension depending on that particular learning algorithm. So here is one example. We are really saying, hey, think of hard margin as VM. So what does that do? If you give it a bunch of training examples that's linearly separable in your feature space, it's going to find a hyperplane that has the largest margin. Okay, so that's a well-defined learning algorithm. And let's say we want to teach that learner, the hard margin SVM, a target model. And in this case, a target model is really a hyperplane. Say the green hyperplane in 3 dimensions. Okay. And let's further say that the teacher has the ability to do constructive teaching, meaning the teacher can pick arbitrary items in the feature space. Now the question is, well, what's the smallest training set and what do they look like that will result in this target hyperplane? If you think about it, you can certainly do it with a lot of examples by forcing the examples to line up with the hyperplane. You can probably do it with 2. Two examples. The trick is you place the 2 examples so that the line between them bisects and is perpendicular to your target hyperplane. We have here something that shows that for hard margin SVM, you can teach it with 2 examples. And you cannot teach it with only a single example here. And here's a very interesting contrast. If you think about it, the VC dimension for d-dimensional hyperplanes is going to be d+1, so this is quite different than what VC dimension is trying to characterize. Another example, and this one is not classification, it's just density estimation. And let's say the student is the maximum likelihood estimator. You give it n data points in RD, it's going to estimate a Gaussian distribution. Okay? And the learning algorithm A is really our familiar, maximum likelihood estimate. So the teacher has a target, in this case, parameterized by mu star and the covariance sigma star. The question is how many examples, if you have the ability to construct them, how many examples would you need so that the student can successfully learn that Gaussian? In 1D, it's very easy to think about. You have some Gaussian somewhere, and probably you need 2, right? You need 2 examples, and you can move them and you stretch them a little bit, you can fit it. In 2D, it's similar. You can actually do this. And in general, in d dimensions, you can use d plus 1, which is the vertices of the tetrahedron, to teach such a Gaussian density. And let's move on to something even more interesting. So let's look at learners that are linear in the sense of parameter and feature vector interacting in inner product. And it's regularized. Okay, so this covers a lot of things. This covers, depending on what your loss function is, of course. If it's square loss, you get ridge regression here. If it's hinge loss, you get your soft margin SVM with regularizer. You can also have logistic regression and so on. And it turns out it's not entirely obvious, but it turns out depending on what you want to do, want to teach, we have some characterization of what the minimum number of training examples are needed, even when a teacher can place them arbitrarily. So let me explain the table a little bit. So these are the different learners, different students. The goal here, we have been actually talking about this, which is AD equals, I should put a parenthesis here, equals the singleton set theta star. Okay, that's teaching the correct parameters. Now, if you think about it, for classification tasks, sometimes you don't care about the parameter being the same because you can scale it and get the same decision boundary. So this row is for just getting the boundary correct, but you may be off by a constant in terms of the parameters. What's interesting here is you see a lot of ones. And even for these guys, they depend on lambda, which is a property of the student, how strong the student regularizes. And it depends on the norm of the target parameter vector. But even in this case, sometimes you could still get a 1. So that is saying you could get away by teaching with a single example, even for classification. You will get the correct decision boundary, sometimes parameter, even with one positive example. You don't need negative example or vice versa. And the reason is you could really do that because the student has a regularizer. And that is acting as a negative pull from the training item. So you can still control it with a single training item. Let me show you a simple example where we look at the squared loss. Yes?
Those are sufficient numbers of training items? I mean, in the cases where it does involve the regularization, do you know if those are sort of, in some sense, necessary too?
So this table is sufficient and necessary. Okay, but it involves the regularizer. So here's a very simple example. That's our squared loss, and it's in 1D just to make it simple. Okay. It turns out for this, you can teach with a single example of the following form. Remember, the teacher has a goal theta star in mind. The teacher can construct a training item pair x1, y1, where let's just scale up the theta star where a is arbitrary constant, that's non-zero. So in other words, there are multiple, infinite number of optimum training set, all with size 1. They will all teach it. Y has to look like this, where lambda from the student comes in here. And you can easily verify it by plugging it in and take a look at the KKT condition. So here's an example. If I want to teach a student which actually has a lambda equals 1, that's the regularizer of the student, I want to teach it the target theta star equals 1. Okay? I need to do this. And if you think about it, this dot is right here. That is my target theta star line. Right? It's teaching with something that's wrong. It's not a point on the eventual line. And the teacher needs to lie because the student is shrinking the estimate. Okay, so it needs to do that so that it cancels out that regularizer. And that's the single item teaching set.
Sorry, so the student, after that, he understood that he was
Pardon?
lost, right?
The student, we're under the assumption that the student is very dumb in the sense that it doesn't even know it's being taught. The student is just running whatever standard machine learning algorithm it is. So that's like on top. That's the student. That's it. It doesn't think. It doesn't look at any of the input data and say, hey, that doesn't look like the thing yeah, no.
Maybe the student is smart, but it's with a grain of salt.
That's a very good discussion, and I intentionally avoided that whole thread in the talk because you could get into some really, really interesting settings, and which are very good, where, for example, we could say that the student is expected to be taught. And it looks at the teacher's examples and say, hey, the teacher must be encoding something else in doing that. So you can imagine this kind of game going recursively. And there has been some recent study on that. OK, so we will come back to this example later. OK, we have a quantity known as teaching dimension. And the relevance, especially to interactive learning, is the following. This notion, teaching dimension, is really, really a lower bound that you cannot break. As long as you are in the setting of giving training examples to a learner, then any of your scheme is just by definition going to use more training items than teaching dimension. Okay, so that's number one. It's just the speed limit. An idealized teacher, of course, can achieve that, again, by definition. And many times we have a constructive way to show what the optimum teaching set is. Okay. Now, this, although it's an inequality like this, I want you to think of this as greater in practice. Many times, the teaching dimension is going to be much smaller than whatever you do, including active learning. One subtle thing, though, this is a setting where the teacher needs to be able to provide both X and Y. So if you are very used to active learning, this is different. You cannot let the computer pick X and the human answers Y. Okay. The human has to pick X. Okay. So keep in mind that your interface must allow that. Now, of course, you can generalize teaching dimension to immediately along at least two directions. One is to say, we don't require that the student learn exactly theta star. You could define some notion of risk for the student, and for example, the difference in parameter or difference in classification accuracy in the future, and so on and so forth. You could also generalize the notion of the cardinality of the training set. Instead of that, you could say every item comes with a different cost, so I'm just going to minimize the notion of cost. And you can, of course, compose these two in various ways, either constrain one and minimize the other, or just say it's the weighted average of the two somehow. Now, of course, this could also apply to learners. That's not just batch learners. Okay. Could say A is, a standard perceptron algorithm, and how do you construct an optimum sequence that's the shortest, and so on. Okay, so just to show you one example where we slightly extend this. This is a case where we are restricted, the teacher is restricted to teach using a pool of items. Okay, so these items are fixed and given beforehand. In particular, we're going to revisit the previous classification task, but now let's say it's -1 to 1 and theta star is right at 0. Let the pool be n uniform items from -1, 1. So the teacher must pick from that subset. Importantly, we assume A is not just any version space learner. A has to be the hard margin SVM, meaning that it's going to, if you give it a training set, it's going to look at the innermost pair and put the boundary right in the middle. So the question is, well, given that, what kind of accuracy can you achieve, right, as teacher? First thing, if you use the whole pool, you just give it to the student. We have seen previously you can achieve order 1/n, and that's controlled by these two. But what's more interesting is, if you think about it, because our learner is special, you can actually achieve 1/n², as follows. Teacher should pick the most symmetric pair in that given pool. And you can show that by doing so, you get 1/n² that improves upon just teach with the whole training set. And this is somewhat different than some of you may be familiar with training set reduction, where you have a large training set, you want to reduce it, or as a sample compression scheme. The essential difference here is we actually, as a teacher, we know theta star already, and we're just trying to encode it with our training items. Okay, so that's a very quick overview of what the theoretical study of machine teaching has for the study of interactive learning. Yes?
So you assume the uniform distribution?
Uniform distribution.
Okay. But can you generalize?
I think you can get the same speed as long as your density is bounded away from 0 and 1. In the range of 0, in that range.
If you don't know the distributions.
I think it's just a constant. Oh, wait. Yeah, the algorithm stays the same. You don't know the sample distribution, but you still look for the most symmetric pair, right? And then the question is, how good are those items, right? How good is that pair?
Yeah, the error now, your error was basically based on the distance from theta star. But let's say that it's not based on the distance, based on the distribution that you don't know.
Right. I know. I see what you mean. So you're saying also change the quality measure, so it's not a difference in parameter, but in terms of its classification. Right. That's your, I guess that's the question, right?
Yes.
Yeah. With respect to the unknown p. Yeah. I have to think about it. I think we wrote something down with that. Yeah. Oh, right. Sorry. All right. So if the human can be such ideal teachers, then he can achieve teaching dimension, beat active learning, and importantly, there's nothing for our computer scientists to do, right? We should just run standard passive learning algorithm, wait and let optimum teacher give us the good training set, which is not going to be IID, but we don't care. We take that, we run our algorithm. We achieve what the teacher gives us. All right. So that's like kind of boring. So let's move on to the second part. The second part is, of course, most humans are not ideal teachers. So I'm going to keep using the 1D threshold classification task as an example because it really shows you how crazy human teachers are. We actually run a human experiment. These are undergraduate students. Okay? Their job is to teach, again, in a one-dimensional space, teach a particular classification threshold. Just recall, in that case, we said if it's pool-based teaching or whatever, if it's not, even if it's not, you're supposed to either take the most inner pair close to threshold, or you look for a most symmetric pair, right? So that's the optimal strategy. Let's see how the humans did. So each panel is one of our selected human subject. X-axis is our interval here, so let's say -1 to 1. The color indicates the true class, so you can sort of see where theta star is. Y-axis, these are teaching sequentially. They're teaching sequentially, so these are trials. They're giving the computer training items one at a time. So, for example, this teacher simply says, I'm going to show you something sort of deep in the red range, and then I gradually move my teaching examples in a linear way to that. And finally, when we reach here, is sort of like, just make sure. Give you another example here, right?
So they knew theta star here, right?
They knew to the start,
Were they
exactly.
math, or what were they?
So there's a very elaborate cover story, as any psychology experiment goes. There's a cover story where they actually construct their own theta star. So they have that really very much in mind. So yeah, they know that.
And they know what the learners have.
That is a very good question. Let me say this. We tell them what the student or the learner is doing. We are not sure everybody understood it. These are not computer science undergrads, let's say. But I will come back to this later, because everybody here is thinking, yeah, that's one failure mode where the teacher really doesn't know what the student is doing. All right. So, yes, sorry.
There's a penalty for them for having too many.
Yes. Well, not really penalty, but we emphasized it in instructions multiple times. Please give us the smallest, training set that you think will teach the computer. Yes.
It seems, I'm just looking at the graphs, it seems that they sort of assume that the learner has no hypothesis class, right? They just sort of try to cover the entire space. So possibly if you just told them you have to only use 2 or 3 examples, they might have done something.
That is a very good condition we didn't run. I should say that these are selected. What I didn't show you is these accounts for maybe, I would say, 30% of the subjects. Another 30% really do have a notion of you're supposed to teach, symmetrically in some way, although very few people actually just give 2 examples. Many times you will see for the other 30%, they're giving 2 examples, but then they want to make sure, so they give 2 more, but also symmetric, and so on and so forth. Then there is the remaining 40% who are just totally crazy. It's even worse than this. This you can sort of see they're doing linear scans. That I don't have any justification. Okay, but so yeah, they're doing many different behaviors. Okay. So faced with this, there are several ideas that I think can be useful for making the teachers more like ideal teachers. The first one is to control them, but let me explain what this is. Here is the algorithm. Very simple. It says this. So this is an algorithm that the computer runs that it is ready to receive teaching from the teacher. The essence is this. It's going to say the first teaching dimension iterations, I'm going to let the human give me XY pairs. Okay? So this is meant for the computer to allow really ideal human teacher that happens to know how to teach with just teaching dimension items. Okay. And the teacher can just break out of this at any time. After that, the computer takes control back and forces active learning on the teacher, okay, until completion. That's it. So allow teaching dimension number of iterations where the human can propose item label, then run active learning if the hypothesis space hasn't been uniquely identified to a single hypothesis. So why do we do this? Well, let's say these are 3 things. That's the algorithm I just showed you. You could also just straightforwardly run active learning, or you could just let humans do their thing, give you X, Y for all the time, right? But let's consider 3 kinds of human teachers You could have some human teachers that are ideal, that knows like, hey, this is a 1D threshold problem. I really just need to give you 2 examples. Or ignore this for now. Or you can have really bad, naive human teachers who are bad in the sense that they don't know what are the good examples X to give to the computer. But still, they're noiseless. They always give the correct label Y for any X. Okay, so that's that. Okay, so let's look at this. For the ideal teacher, here's the bottleneck, right? We shouldn't subject an ideal human teacher to active learning. Remember, active learning complexity is greater than teaching dimension. And that shows here. If you have real good human teachers, you should let them do their thing. Or that algorithm can also let them do that. In contrast, if the human really isn't very good at teaching, running active learning is a great thing. Okay? Because if you let them do their own thing, sometimes they do this, right? They just think they will give you a few positive examples, and they think they showed you the classification problem very well. They don't realize that you're supposed to give some negative examples to determine the decision boundary. Okay, that's why there's an infinity here. That just means it takes a very long time, and they may not complete the classification task. But if you think about the algorithm I just showed you, we have a fallback guarantee in that you waste the initial TD iterations, and afterwards you still have active learning. Then you can force the human to eventually do the right thing. Okay? And because teaching dimension is less than or equal to active learning, you get a factor of 2 at most here. So that's your guarantee. That's one thing. Second, I want to say something about there's a very interesting group of users who are not ideal teachers. So they are still doing bad things here, but they know to provide one item in a possibly very small positive region. If you're familiar with active learning, you know the concept class of a single interval is very hard to learn because the interval could be very narrow. And if you run active learning, you don't have a good way to start with. You have a cold start problem. You need to find that interval. So that is almost like random search in the beginning. But once you get one positive item inside, you probably get many negative outside. You immediately can start binary search on these 2 boundaries. Okay. So the story here is, for some humans, if you allow them to give you both X and Y, they may be able to give you some seeds. And in doing so, warm start your active learning algorithm. And this is actually a very expensive part for active learning. So that's still very good use of human power. Okay, let's see, 5 minutes, 10 minutes? Oh. So let me show you some real experiments. So here, by Turkers, I mean human teachers. Okay, they are teaching us this 1D problem. Actually, we have 2 problems. One is 1D threshold. The other is 1D interval, as I showed. There's a target interval. In each plot, the x-axis, these are the number of iterations that's needed for the teacher to fully specify the concept. And the y-axis is just a histogram. So what are we saying here is there are 3 conditions. Human condition is when you allow humans to just provide XY pairs. That's it. So let's look at 1D threshold task. We know a good teacher, ideal teacher, should just be able to provide 2 examples. And we do have some subjects who are like that. And we have a few more which provided some extra items. But the real bad thing is here. There is a very significant fraction of human subjects, human teachers, who were unable to teach the concept, mostly because they didn't think they need to provide negative examples, or or maybe they provided examples, but there's still a very large leftover uncertainty version space in the middle. Okay. While in contrast, if you run active learning, for this particular task, it's actually discrete with like 1,000 X values. So you get 14 questions. That's the number of binary search questions you need to ask. So everybody gets that. If you run mixed initiative, you sort of get an improvement in the sense that you preserve these smart teachers. But you force those ones who cannot succeed to be around here. They're around here because they have to run active learning, but they will have to, consume the first TD dimensions, then run active learning. So you get a small tail here, but this is much better than this no count, which means infinity. Similar things is happening for the 1D threshold case. So that's that, using a special algorithm with certain guarantees to force the humans to, be good teachers. The second idea is to educate them. Okay. The idea is very simple. You want to show them what optimum training set look like so they can do that. But of course, they're trying to teach you, right? They're trying to teach you theta star, so you don't know what theta star is. What you can do is to pick an arbitrary theta prime from the hypothesis space and say, hey, if this were the concept you try to teach me, I, as the computer, I can compute what the optimum training set would look like, then I will show that to you. So in the one-dimensional threshold case, this is a real example of what a education might be. So the computer picks an arbitrary threshold at this number, and it knows that these two are the teaching set. It just generates a natural language sentence for that human. So that's that. And how does it do? So we have anything plus analog. This is human received that training. It's really just in the form of showing a bunch of text sentences before they do their teaching. That's all. Okay. But you see that, so look at the dark purple. That's how much of them are actually producing the optimum teaching behavior afterwards. So in all these cases, the dark is increased. Finally, this is getting to probably the more interesting part. Maybe the humans are, near optimum teachers, but they just don't know exactly what your learning algorithm is. So they may be teaching with respect to something else. And maybe you, as a computer, you can have a meta-learning algorithm that translates what they're trying to teach you into a form that your actual learning algorithm can accept. I'm just going to show you a super simple example so we know what it is about. Again, this is the one-dimensional linear regression, ridge regression task. So here the student regularized these squares. Importantly, the regularization strength lambda, that's a property of the student, so it's part of that student. Okay? Now the human comes in and human says, hey, I want to teach you that theta star is 1, 45-degree line. But I, as the teacher, I have a wrong idea of what your lambda is. I thought your lambda is 1, so this W is wrong. Lambda wrong is 1. Well, actually, the learner has lambda star being 2. So if I don't know the correct lambda, I start with this. I will get our optimum training set construction. We have seen this before. It's just going to be 1, 2, the red dot previously. The student, in this case, would actually learn a wrong theta because the student is running with lambda star. Okay. So here's a big if. If we have reason to believe that, or actually if this meta-learner knows both lambda w, the wrong model in the teacher's head, and the correct lambda star that the learner is actually using, we can take the human example here, that's x and y, and transform it into x tilde, y tilde in the following way for linear regression. And that turns out to be 1 and 3. Now, if you give 1 and 3, of course, the student with lambda star will learn the correct theta.
So where is this translator?
Pardon?
This translator in the middle? How?
Translator in the sense of translating x, y, the example that human gives us, to something that, to x tilde, y tilde, to a
So
different
you have access to this translator.
We're assuming like we can do that, right? The translator is the meta algorithm that we need to build.
Right. Because if you have access, so basically you know what is lambda.
Exactly. You could say that
Start from that.
I could, if I know lambda w already, I could already run it with that, immediately interpret what the human is trying to do. Okay. So I think this certainly the idea is not realistic as is, but it might be useful in terms of when we know roughly what the teacher is teaching. Maybe roughly speaking, the teacher is viewing the student as, say, Gaussian mixtures. Okay. While in reality, the student is running, say, an SVM. Okay, to summarize, humans are teachers. Treat them as teachers. You can get more information from them. And the study of teaching dimension gives you what they can do in the optimum sense. Even if the real teachers are not optimum, there may be some ways here and some other ways that you can help them become better teachers. That's it.
So one interesting thing in these human study experiments might be to include some people who have teaching experience and see if that, if that actually alters the kind of strategies that they use.
That's a very good suggestion. And in fact, we didn't do that just because of the difficulty in recruiting actual human subjects. But we did ask them, like, do you have teaching experience, or are you a parent? We didn't see huge differences in the kind of task that we studied, but perhaps because the tasks are too artificial and not similar to real-world teaching tasks.
So can you comment on the role of adaptivity? So in learning, letting the next example depend on any observations made in the past. There's an exponential gap, at least in certain settings, right? What about teaching, right? So if I understand correctly, in all the examples you gave, the teaching set is chosen non-adaptively, right? So you specify the communication between teacher and student is one way.
Yep.
The teacher keeps saying something, in the end, hopefully the student got the right answer.
Yeah, that's a great question. It is one way simply because we assumed a well-specified learner, and it's just going to be there. So I think the question can be decomposed in two different ways. Let me try one way first. Let's see if it works. One setting in which there needs to be adaptivity from the teacher's side is when the teacher doesn't know exactly what the learner is. And one example could very simply be this, where I know, as a teacher, I know a student is running linear ridge regression. I don't know exactly the lambda value, right? I perhaps know lambda is between, say, 0.1 and 100, but I don't know more than that. Now, as you have seen in the examples, I cannot just, in this case, blindly create a single dot and teach it, because what learned depends on the student's lambda. But you could imagine, in this case, allow adaptivity in the sense that why not let the teacher maybe teach a little bit, but then probe the student, right? In a sense, like I can ask the student, hey, here comes an x equals 10. Please tell me what you predict as y. Okay. In that simple example, if there's no noise, just one probing would give you exactly lambda, right? And then you can say, after that, there's a question of like, do you need to clear the learner's memory and start from scratch and say, here's a new example. Now I know what you are and I can teach you. Okay. More interestingly, when the probing only gives you partial information because of, say, noise, this sounds a lot like active learning from the teacher's side. So then we have perhaps an interleaved active learning and optimal teaching going on. And I think that's great research.
So, quite related to this, I guess one idea would be to have the learner giving some feedback about its current state of knowledge. It's at minimum like an uncertainty region for the version space approach. And so, I mean, in some sense, that might make at least the worst cases sort of like doing active learning anyway, because you're only giving samples in the uncertainty region, or maybe even some scores. And then,
yeah, I think that's right. I think that's right.
In the plots that you showed of people trying to train the interval and zigzagging and different things like that, these plots kind of suggest that the trainers here are assuming imperfect memory on the learner or something, right? And of course, when you're teaching humans, that's a pretty decent assumption.
Yes.
So is there a way that you could design an experiment to kind of tease apart the effect of the imperfect memory assumption?
Yes, I think this is, well, I mean, I shouldn't say yes. I haven't thought about like what exactly the experiment might be like. But it is true that the fact that a teacher is compelled to give you a lot of examples kind of is saying, I don't trust your learner, right? You are not doing kind of cutting off the version space kind of learning. You are doing something that's much slower. One example doesn't push you too far, that kind of thing. So in some ways, we can borrow from the literature built in psychology and say, hey, these are the standard models that a human teacher might assume of a human student. Okay. If so, maybe there is also a translation phase later, right? So given this, I can at least condense it. This is easy. I can condense it to the most efficient pair. But for other tasks, maybe there's a different translation, knowing that or assuming that the teacher is teaching a more human-like student with a cognitive model that we can mathematically quantify.
Maybe you mentioned this, but so when you were going through the first part of the talk, you know, there were the ideal targets. So you get the SVM, and you have two kind of equally space symmetrical items. You've got, you know, D+1 and Gaussian learning. So do you give those targets? Do you give those targets to the human teachers in the second task?
So let me.
I think even, you know, like, you know, most people didn't, you know, natively kind of come up with essentially D+1 optimal points.
Right.
Right. But if you basically suggest the target as being D+1 optimal points to learn a 2D Gaussian, or, you know, 2 points to, you know, it seems like that target effectively allows them to start thinking about the teaching problem in a way that they perhaps hadn't before, and elicit information that wasn't even available to them effectively prior to the task.
So let me comment on your observation in maybe two different ways. One high-level comment is, in reality, when we as running, you know, interactive learning algorithms, usually I would like to think like the humans actually has theta star in their mind for some task. Maybe they have a difficulty, you know, articulating what theta star is, but everybody sort of have a notion of, you know, what spam is, right? So that theta star is innate in their mind. Okay, so that's a high-level comment. But second, more to the point of running any actual human experiment, and you need to force a foreign theta star on them. Okay, that's where you need to design an experiment in a way that they, you know, sort of intuitively agrees with your theta star. And this, for example, in the experiment here, we spend a lot of effort making sure like they actually have a theta star in mind. So,
But were they given, so for example, if the target's 2, like if the optimal target's 2,
yeah.
then essentially you'd want to provide feedback at 2. They give 2, okay, here's the theta star.
So sorry, when you say you mean the teacher?
No,
Or?
I mean you, the experimenter.
Okay, I'm the third thing. I see.
You're the designer of the experiment, to try to kind of ideally or optimally, anyway, it seems like essentially providing them with, as you were describing the lambda, or here, essentially the predicted theta at each of these, exactly how well is this doing, given random x.
You are saying we as experimenters, we need to first teach the teacher about theta star, then they can teach the computer. Maybe that's what you're going at.
Right. Yeah. Well, I mean, if we're trying to optimally, I mean, you have these 3 kinds of ways in which you're going to instruct the teacher at the end, and it seems like none of them are really getting at precisely the task that you set up as the ideal maximum in the first case. That's all.
No. So the ideal maximum, the ideal training set is with respect to some theta star that's already in their head.
Truly.
So that's that. When you do experiments, you can, for example, for the experiment here, what we actually did is these X items are meaningful items. They're like photos of everyday objects. And the task is a binary task. It's, can you grasp that object with one hand? Okay. And we actually made each individual teacher, human subject, sort all the photos in a linear line, and they mark which ones they can grasp and which they cannot. In doing so, they give us their theta star. All we are enforcing is this 1D structure.
Did you try to have like one teacher and several learners?
Yes. So the setup is the following that we did. We actually did precisely, again, for simplicity, this kind of learner where I have a family of, or rather a class of learners with different lambda values. Okay? Now the teacher is under a setting that they have to teach the class of students with the same lecture. Okay, so that's the same D, right? Now you have to define or extend the notion of optimality. You can do average, but what we did is minimax. So the worst student would have some kind of performance guarantee. And if you do that, you can solve things in closed form still for this learner at least. What you see is, number one, the teacher is teaching in the middle. It's teaching the middle student. And second, the effect or effectiveness of teaching worsens if you have more academically diverse students in the class, which I think agrees with our intuition.
One last question, and then we'll break for lunch.
I was just wondering about, like, you gave this detail about the images and like how capable the object is, right?
Graspability. Are you talking about this 1D, sorry, the 1D experiment?
The 1D experiment
Yeah.
when the images have to be sorted and whatnot.
Yeah.
So that could also explain some of the zagging behavior, isn't it? Because the teachers might be thinking that, well, the student has really no idea about like in what way I've sorted things, and like symmetry and distance is not naturally occurring to them. At the end of the day, it's only a ranking that they are providing, so they might be thinking, well, I have to teach the full ranking, right?
I think that's a very good comment, and it's getting into, it's just difficult to run human experiments. In my defense, we didn't invent this linear scale. This is a common, task used in psychology, and other people normed it. So it's the same set of photos. They got thousands of undergrads. They asked them to place these things in a linear order. So they come up with a linear sort of, there's a reasonably linear scale that we know from prior work. But that said, yes, yes, exactly. So what you said may still be true. I mean, that may still drive some of the teaching behaviors.
Okay,
Why don't we thank Jerry again? First afternoon talk will be at 1:30, so we have about an hour and a half for lunch.